So these next two videos will be about the fundamental theorem of calculus. The fundamental theorem of calculus is split into two parts, so this particular video will be focusing on part 1. So what the fundamental theorem of calculus part 1 essentially tells us is if the function f of x is continuous on the interval a to b, and if capital F of x is the antiderivative of f of x on the same interval, then this formula will hold true. And what this formula basically is saying is that the definite integral can be determined by subtracting f of a from f of b. So what this basically means is you plug in both your a and b values into the antiderivatives of the function and then subtract f of a from f of b to solve the definite integral. This allows you to find the area under the curve on an interval from a to b quite easily. So in this formula it's kind of missing a step with a special notation, and that notation is written right here. So when you find the antiderivative of f of x here, you'll end up with a capital F of x and with this line. And what this line from a to b essentially means is the same thing as f of b minus f of a. So this is a shorthand way of writing this right here. So before we get into an example problem with using the fundamental theorem of calculus, we'll talk about some basic integral formulas that will help us solve some integrals first. So the first one is x to the n, the integral of x to the n, and what this equals is x to the n plus 1 over n plus 1 plus c. So this is a pretty common formula, and it's one that you use very often, and it's one that we'll use in our example problem down here. Next, we have the integral of sine x, which equals negative cos x plus c. And finally, we have the integral of cos x, which equals sine x plus c. So these formulas will help us with many of our problems. So here is an example problem for the fundamental theorem of calculus, part 1. So first of all, we should use our first formula here to determine the antiderivative of f of x, which is this function. And what this should equal is capital F of x evaluated from a to b. And so when we work that out, we will first deal with the 12x to the 5. So x to the 5 plus 1 will give us x to the 6, and divide by n plus 1, and 12 divided by 6 is 2. So we have 2x to the 6. Then we do the same thing to 3x squared. We end up with x cubed, and then divided by 3, but 3 divided by 3 is 1. So that's all there. And then the 4x, the x becomes x squared, and then 4 divided by our 2, n plus 1, is going to be 2. And we have to draw the line again. And in this case, our a and b values are 0 and 2. So you write those in their respective spots. And so now what we need to do is plug in our a and b values into our f of x antiderivative, and by doing that we will be able to determine the solution to this problem according to the FTC. So what's this going to equal is 2 times 2 to the 6 plus 2 cubed minus 2 times 2 to the 2. And that's going to be minus 2 times 0 to the 6 plus 0 cubed minus 2 times 0 squared, because our a is 0, and this can be disregarded because it will just equal 0. So then if we work this out here and do all of our work to find that, we will end up with 128. So this is the solution to the to the definite integral. And what this 128 represents is basically the area under the curve on the interval from a to b, which in this case is from 0 to 2. So that is essentially how you use the fundamental theorem of calculus part 1. It is not as difficult as it looks, and stay tuned for part 2. As always, physics is awesome.